All right, everybody. So I'm recording now. Hey, you did a great job in those breakout rooms. Everybody built those figure 4 and figure 5 just right. Does anyone have questions on that before we move on? Okay. And can someone give me their description of how uh, that pattern was growing? Two blue stars are added to each figure. Two, I like it. Blue stars are added to each figure. Yeah, so we can see, for instance, that as we move from figure uh, 1 to figure 2, we added these ones. As we moved from figure 2 to figure 3, we added these ones. Yep, awesome. And then that would continue. And in our table, you did this just right. 3, and then 5 and 7 and 9, 11, 13, and 15. And so what you can see is that we're adding one figure and then we're adding two stars. Adding one figure, adding two stars. Adding one figure, adding two stars. And it just continues like that over and over again. So great job seeing that pattern. Now I'm going to do a little instruction here. So this would be a great time to be taking notes. I'll let you get set up for taking notes. All right, so when we're talking about linear relations, we can think about it in terms of patterns, in terms of graphs, equations, and tables. And it doesn't actually just have to be patterns of tiles, it could be all kinds of different patterns. And so in graphs, these linear relations always show up as straight line relationships between two variables. So, like x and y. And the x is often called the independent variable, and the y is called the dependent variable. I'm just telling you that right now. You don't need to get it in your notes, we'll get it in later. Equations can be written in this form. All linear relationship can be written in the form y equals mx plus b. Give me a thumbs up if you've seen y equals mx plus b before. Good, Sophia. Great. Glad to hear it. Awesome, Will. Great, Elisha. Good, good. Elliot. Thank you. All right. So m, remember that m, that's the slope. And the b is the starting value or the y-intercept. Really, the technical term is y-intercept, but we think of it as starting value very often. I bet that's what your teacher referred to it as. Anybody, did they refer to it as the starting value, y-intercept, or both? Both. All right, great, great. I like that. In tables, just like we saw in that warm-up, as the x grows by a constant amount, oh, I don't know where the y went to. This should be y also grows by a constant amount. So the ratio of change remains the same. Uh-oh, Jade's gone. Hopefully she comes back. So we're going to look at each one of these now. So here on the left, these are all linear relations. Straight line, straight line, straight line, straight line. And on the right, these are not linear relations. Here it looks like a straight line, but then it curves. looks like a straight line here, and then it curves. This one's curvy all the way through, and this one is also kind of curvy all the way through. So that's what I mean by a straight line relationship for linear relations. Any questions on those? Okay. When it comes to equations, now this can be a little bit more confusing, so please do ask questions. We can always write linear relations in this form, y equals mx plus b. We can always do that. But sometimes we get linear relations that are not written in y equals mx plus b form. Now, the important thing to notice, both of these are not in y equals mx plus b form. The important thing to notice is that there is, you can have a number multiplied by y and by x. Any number is fine, but notice that we're not raising our x or our y to a power like we are here. So these are non-examples of linear relations. So this one has this x squared. That in and of itself would make this a non-linear relation. But also this square root over the x over here, that's also a problem for linear relations. So notice that doesn't happen in either of those. So this x squared makes this one not a linear relationship, and this square root x makes this not a linear relation. There are other ways that we can have equations that are not linear relations. We could also have x in the denominator of an equation. That would also not be a linear relationship. Questions on equations and how linear relations show up in equations. All right. In tables, here we can see that x is increasing by 1 over and over again. And we can also see that the y value is increasing by 2 over and over again. So that is a linear relation. Down here, we have our x increasing by 1. And I'm just going to use the same colors as long as it's doing the same thing. And our y is decreasing by 4. So that is also a linear relation. Notice it doesn't matter if it's increasing or decreasing. Notice it doesn't matter where you start. Here in the table, we started at 1. Here we started at 5. That's just fine. In this one, this is also a linear relationship. And notice that we're actually not increasing by 1. We're decreasing each time. And in the first one, this is a decrease by 1. But then this is a decrease by 2. Let's see, I'm going to do that in a different color, I think. This is a decrease by 2. And this is a decrease by 2. So we are increasing by 0.5 there, and we are increasing by 1 there, and by 1 there. So on this graph, or this table, excuse me, when we increase by 1 in our x's, we increase by 0.5. And notice that that's the same ratio as when we excuse me, did I say increase here? I believe I did. when we decrease by 1 in our x's, we increase by 0.5 in our y's. That's the same ratio as when we decrease by 2, we increase by 1. Notice here we're multiplying by 2, and here we are also multiplying by 2. So this is also a linear relationship. Does anyone want to ask a question on that one? It might be a little bit more confusing. I tried to throw a little one in there that's a little bit tougher to maybe get some conversation going. No? All right. On this one down here, as we increase by 1, those are all the same. Here we increase by 1. Here we increase by 2. And here we increase by 3. So that cannot be a linear relationship, because on the x's, it's staying the same. We're increasing by 1. But on the y's, the change is changing. So our rate of change is not constant. Here our rate of change is constant. Here our rate of change is constant. Here our rate of change is constant, even though what we're changing our x's by is not. It's okay. Here we're increasing by 1, increasing by 1, increasing by 1. Here we're increasing by 7. Here we're decreasing by 10. And here we're increasing by 7. So that cannot be linear. Increasing by 1, increasing by 1, increasing by 1. Here we're increasing by 7. Oh, did I just do the exact same table? I did. Well, that's useless. I don't think you're going to learn anything from that one that you learned from the previous one. Sorry about that. Questions on those tables? All right. I'm going to pause our recording right here.